Hello everyone and welcome to lesson 23 of the Save My STEM Physics channel. This is going to be the first lesson of mechanics, year 12 for AQA A-level physics, and we are going to be talking about motion graphs, which contains two types of graph, displacement time and velocity time. So a displacement time graph is is a graph which looks something like this. So there's a positive section and a negative section with only a positive amount of time along the x-axis, the y-axis representing displacement. Obviously time cannot be negative, which is why we don't extend it back here. So if we have a point, time equals 0, the initial point will almost always be at 0 displacement, because displacement is taken from one point, the distance from one point. And so if we say have someone's displacement being a straight line up, and then their displacement continues to be the same, that should be a horizontal line there. It's slightly not. I apologize for that. And then it sort of does something like this. This is what we call a displacement time graph. Actually, let me just label the axis as S for displacement and T for time. So here we see that their displacement is increasing. Here their displacement is the same, and then it's decreasing. It's the same, and then it's decreasing. But importantly, I'm going to split this decreasing section into two smaller sections. So first, if their displacement increases, so up S increases linearly, so with a straight line, that means that their velocity is constant. And the relationship between the velocity and the displacement is that velocity is the rate of change of displacement, or meters per second, because displacement is a distance, and rate of change is measured in a unit of time, seconds. So V equals meters per second, and most importantly, we can find the velocity by doing the change in y over the change in x, which is the gradient, something you have probably met at GCSE, or hopefully met at GCSE. And the reason that this works is because delta y is in meters and delta x is in seconds, but using our power laws, we know that if something's over a variable, then that is the same as saying that multiplied by the variable to the -1. Thus we get meters per second. So this is what a displacement time graph looks like. A displacement time graph may also have non-linear sections. So their displacement may look something like this, which isn't a perfect graph, but you kind of get the gist, where they have an increasing velocity here because the gradient here is steeper than the gradient there. So they must have an increasing velocity. Here I've tried to draw as constant velocity, and then it begins to curve here with actually a decreasing velocity there. One thing to note on both of these graphs is I will actually extend that out further just to make the point very clear, is that they can go into the negative displacements. It's just that when it crosses the x-axis, that just means that it is going through the original point, basically, because displacement equals 0, so it must be going through where displacement equals 0, which is the original point. If the graph is a horizontal line, we cannot physically take the gradient of that. Oh, sorry, no. We can take the gradient of that to be 0, because its change in y is 0, but its change in x could be any value. And it would still be a gradient of 0. So that means that it is not moving, it is stationary. Um, and yeah, so that is displacement time graphs. If it's a horizontal line, it's stationary. If it's a straight line up, then it's got a constant velocity upwards, constant positive velocity, I should say. If it's got a straight line down, it's got a constant negative velocity, and depending on the shape of a curved line, it may have an increasing or decreasing velocity. So those are the important notes for a displacement time graph. But now, what if we map the gradients of these? So taking from this one all the way at the top, let's make a velocity time graph. So the velocity time graph is just going to be the gradient of each point here. So the gradient here, we can say is probably about 3. Hold on, let me mark this up. Let's say this is about 3, and it's a straight line because the gradient is constant. And then it shoots down to 0 because it has 0 velocity at that point in time. And then it will begin to have a negative of about also 3. So we'll display it like this. And then it will be stationary again, so we'll move back up to the x-axis to say that it has a velocity of 0. And then it continues to have a negative velocity of about 3. And so that is where our velocity time graph comes from. It is merely just a mapping of the gradient of our displacement time graph. So those are how velocity time graphs work. They show us how fast something is moving at a moment in time. We could also do it for this graph here, where we can do so. It starts off with quite a small, but actually goes up. So that can be sort of drawn by this straight line in time here, and then it's stationary, and then it begins with a constant negative, which starts ever so slightly getting decreasing with time. Sorry, that's incorrect. It's more something like that, because we will see on this one that it starts ever so slightly approaching a horizontal line, which means that its velocity must be approaching 0, so it must be getting close to the x-axis. Please ignore this line down here. And yeah, so those are velocity time graphs, those are what they describe. We have already discussed that the gradient of the top graph mapped is the bottom graph. But how do we go back? If we take the area underneath these points, then we can actually get back to this one. So the area in this time, on this velocity time graph, in this little rectangle here, is equal to the distance travelled. If I just move this back down, is equal to the distance travelled at that point, or the displacement, I should say. So finding the area underneath a velocity time graph helps us find the displacement. And what we should find, I haven't actually drawn this very accurately, but what we should find is that approximately here, and so if we take the area of these sections, so that section, and that section, if we add these sections together and take them away from that section, their total area should be 0. Since on this graph, our displacement is 0 here, and these sections map the displacements given for each velocity and time. So that's how we go back from a velocity time graph to a displacement time graph. The last thing that we need to note about velocity time graphs is that their gradient is their acceleration. So A is in meters per second squared, and we can take the exact same logic of delta y over delta x, where delta y is meters per second, and delta x is in seconds, which means that we get again meters per second squared, which is acceleration. And so it has a constant acceleration on this line here, and it has no acceleration there, and no acceleration there, and a constant acceleration there. Again, the same point will follow, where it may actually have a changing acceleration, which is represented by a curved line either like that or like that, and which I've just drawn down there. And the gradient at any given point is its instantaneous acceleration. You could take an average acceleration by going and finding the acceleration between the 2 points using a line, but frankly that's not very accurate and physicists don't really care for it very much. So those are velocity time graphs, those are displacement time graphs, and those are how to translate the two of them. So I hope this has helped a lot, and the next few videos will probably be very maths focused. So yeah, I hope you will enjoy and understand. Thank you very much for watching. Bye.